We're now going to look at optimization. The idea of optimization is we have something that we want to either maximize or minimize, and we're going to try to figure out certain conditions. The first thing we should do in optimization is to sketch and label a diagram. The next thing is to look for relationships in geometry. This can be formulas for area or perimeter, or it could be something like the Pythagorean theorem. We then need to formulate the objective function. Actually write down the function that you are trying to either maximize or minimize. And then finally, we can actually find the maximum or minimum depending on what we're looking at. So let's look at an example. Let's suppose we want to fence in an area where one side is along a river and we don't want to have to fence in the side along the river. So we just need 3 sides to our rectangle. And we know we have 500 yards of fencing. And we want to maximize the area. So we want the maximum possible area. So what are the dimensions? Well, let's call this X and Y. We know we have 500 yards of fencing, so that's going to look at our perimeter. So 500 has to be 2y plus x. Remember, we don't need to fence in the side along the river, so we only have 3 sides. And we know we want to maximize area, and area is length times width. And essentially what we're going to do is solve this first equation, the perimeter equation, for one of our variables. I'm going to go ahead and solve it for x. So 500 minus 2y is x. And then I'll stick that into my other equation, my area equation. So 500 minus 2y times y. Or 500y minus 2y squared. So this is my function that I now want to maximize. And we find the maximum using the first derivative. So let's find the derivative. The derivative of 500y would be 500. The derivative of 2y squared is 4y. I then need to set this equal to 0 and solve. So 500 minus 4y. That tells us that that tells us that y is 125. So now we have one of our 2 dimensions. Our second dimension is going to be very easy to find. 500 minus 125 times 2, which is 250. So these are the dimensions that will give us the maximum possible area. Let's look at another example. Let's suppose that we are designing soup cans. And we know that the material for the cans cost 0.0003 cents per square centimeter. And we also know that the can must hold 400 milliliters of soup. So what do we need to do to minimize the cost? We don't want to spend a bunch of money. So how can we minimize the cost of material? Well, we have 2 dimensions here, R and H. We know that the volume of a cylinder is pi r squared h. So I have 400 is pi r squared h. The material is just going to be on the surface area. And the surface area of the cylinder is given by 2 pi RH plus 2 pi r squared. So this one's going to be a little more complicated. Let's solve our function, our volume function for h. I then have 400 over pi r squared is equal to h. We can then substitute that into my surface area formula. So now I have 2 pi r times 400 over pi r squared plus 2 pi r squared. Simplifying is going to give us 800, and I'm going to write this as r to the negative 1, plus 2 pi r squared. In order to maximize or minimize, we're going to want to take the derivative. We bring the exponent out front and subtract 1. And then the same thing on the right. Bring the exponent down and subtract 1. We now need to set this equal to 0 and solve, which is a little more complicated. So here's the equation we need to solve. And in fact, what our first derivative test tells us is that this is going to be either a maximum or a minimum if our derivative is equal to 0 or doesn't exist. So we also need to include the case that r is equal to 0. This is one of our critical points. Let's go ahead and multiply through by r squared to get rid of the fraction. We then have 0 equal to negative 800 plus 4 pi r cubed. We can add 800 to both sides and divide by 4 pi. We now have 200 over pi equal to r cubed. So r is going to be equal to 200 over pi, and then we're going to take the cube root of that number, which is approximately 3.99, so we'll go ahead and say 4 centimeters. We also need our height. And we did have a formula for height that was 400 over pi r squared. So 400 divided by pi times 4 squared gives us that the height is approximately 7.99 or 8. So now I have both my height and my radius. So now we know exactly what dimensions will minimize the cost, and we can actually calculate the cost of that can if we want. That's where the cost per square centimeter came into play.